Okay, everybody, welcome to lesson number 4. Today you're going to learn about your new best friend, the ICE table. The ICE table is a nice tool we have to help us organize our information when we're trying to solve an equilibrium problem. So we're going to look at how it can help us solve the following problem. So here we've got an equilibrium situation. Iodine monobromide is decomposing to produce bromine and iodine. The information we're given is that a certain number of moles, 6.5 moles of iodine monobromide, are placed in a closed 1 liter container at 150 degrees Celsius. So that's that temperature that pops up in these questions. So again, we're not using it in our calculations, but they will always report it. So you can imagine a closed container. There's a closed container, and we're placing some IBR inside that container, 6.5 moles. The volume of the container is 1 liter. And when we leave that iodine monobromide in there, it's going to decompose. So if we leave this and some time passes and we come back, we'll see that there will be some IBR present because it's an equilibrium system, but we'll also find some iodine and some bromine in there. Okay, so this reaction is going to happen inside that container, and over time we're going to find that what's in the container changes. So the volume's still 1 liter, of course. So we have one additional piece of information which is important in helping us identify the way we can solve the problem. And so here it's reported that at equilibrium, the concentration of bromine is known. It's measured to be 0.5 moles per liter. So bromine concentration is known at equilibrium, and the others are not, according to the information that's given. So, if we take a look at what's being asked, we have two questions here. First, what are the concentrations of iodine and iodine and iodine monobromide at equilibrium? So that's something that they want us to find out. They're not known, but we can find them out with the information that we have. And second, we're going to calculate the value of KEQ for the reaction, which is something that you've done before, but the difference is we're not given those concentrations. We need to find the concentrations before we can do that calculation. So, your friend, the ICE table. I've got a little ICE table drawn out down here. So here's the balanced equation for the equilibrium that we're looking at. And as you can see, I in the ICE stands for initial concentration. So that's our initial concentration of our reactants and products when we get started. C is the change in concentration of those things over time. And E is the concentration of those things when equilibrium is reached. So if you consider your activity with the straws and the water, this is analogous to the initial volumes in the cylinders. This line tells us how those volumes change over time, and the last line tells us what those volumes are when equilibrium is reached. Okay, so that's a nice analogy to look back at. So, to start filling this out, we want to check and see what our initial concentrations are. So if we go back to our given information, we are told up here that for iodine monobromide, we have 6.5 moles. So N for moles, and the volume of the container that we're in is 1 liter. Molar concentration, if you recall from grade 11, is number of moles divided by volume. So we have 6.5 moles in 1 liter, and our concentration is 6.5 moles per liter of IBR when the reaction starts. So we're talking about these initial conditions here when IBR is the only thing present. This step might seem very trivial because 6.5 moles divided by 1 is 6.5. However, if this container is not a 1 liter container, but it's a 2 liter container or a 500 milliliter container, we're not going to get 6.5 for our answer. So it's not it may look like a trivial step, but if you miss this step and you get the wrong concentration here, you'll be in trouble. So make sure that you take the time when you're looking at your initial conditions to calculate that concentration. So now we can put that number into our ICE table. So we know that when the reaction's beginning, I'm just going to fill in the top here. So we've got concentration of IBr, concentration of bromine, and concentration of iodine. So when the reaction's beginning, inside our closed system, we have 6.5 moles per liter of IBr. We have 0 moles per liter of bromine when the reaction starts, and 0 moles per liter of iodine when the reaction starts. It's not always going to be the case that you have things that are 0. Sometimes you are given 3 starting concentrations for this type of problem. But in this case, we don't have any of those things to start with. Next, we draw our attention to the change line. So how are these concentrations going to change over time? Well, for bromine and iodine, the only way these concentrations have to go is up. They are definitely going to increase because right now we don't have any. There are none. So we're going to write plus signs over here to indicate that those concentrations are going to increase. And the iodine monobromide is definitely going to decrease in concentration. So we're going to put a negative sign over here because this 6.5 moles per liter over time is going to go down as the IBr reacts. Next, we have to think a little bit about stoichiometry. So we've got a 2 up here, a coefficient of 2, and it is understood, of course, that the coefficients are 1 for bromine and iodine over here. So I'm going to erase them, but they are 1. So the mole ratio in this reaction of IBr to Br2 is 2 to 1, and IBr to I2 is also 2 to 1. If 2 moles of IBr react, we're going to produce 1 mole of each of these things. Okay, this is important because if this reaction is going on, that stoichiometry, it doesn't go away. It's happening all the time. So in our change line, we don't know what these concentrations are changing by, so we're going to use x as a variable to represent that change until we find out what it is. But IBr is going to go down by a value of 2x, and Br2 and I2 are going to go up by a value of x. Okay, so the reduction in concentration of IBr is twice as big as the increase in concentration we get for Br2 and I2. So very, very important to include that coefficient in your change line. Finally, for equilibrium concentration, here we have 6.5 moles per liter minus 2x. If we can figure out what x is, we can figure out what the final concentration of IBr is going to be, because this concentration is going to decrease as the reaction goes forward. For bromine and iodine, the final concentration is equal to 0, the initial concentration, plus x, which is equal to x. So I'm going to write it out. 0 moles per liter plus x equals x. You don't have to write that out if the initial concentration is 0, but you can. So at equilibrium, the concentration of IBr will be 6.5 moles per liter minus 2x, and the concentration of Br2 and I2 are equal to some value x. So x is standing for a concentration that we just don't know what it is yet. Now, there are many ways that we're going to solve for x during this unit, but this question here is lovely because we're given this additional piece of information. At equilibrium, the concentration of Br2 is measured to be 0.50 moles per liter. So that is a key piece of information, and I'm going to write it down here. So we know that at equilibrium, the question tells us the concentration of Br2 is 0.50 moles per liter. From our ICE table, we know that at equilibrium, the concentration of bromine is equal to x. So if the concentration of bromine is equal to 0.50 and it's also equal to x, therefore x is equal to 0.50 moles per liter. Okay, so those things are all equivalent to each other. So with this question, it's actually giving you the value for x, and we'll see in future lessons that that's not always the case, but it's nice for us in this instance. If the concentration of bromine is equal to x is equal to 0.50 moles per liter, then we can answer question A. So what are the concentrations of I2 and IBr at equilibrium? The concentration, so all of this is helping us answer question A. You can see my answer at the bottom. The concentration of I2 is also equal to x, equals 0.50 moles per liter. It makes sense that they're the same because we start off with 0 and they're both going to increase by the same amount because they have a 1-to-1 mole ratio. And finally, the concentration of IBr is equal to 6.5 moles per liter minus 2x, so 6.5 moles per liter minus 2 times 0.50 moles per liter. And just to be clear, since x is equal to 0.50 moles per liter, I'm just subbing in that value here. And what we get as our final answer is 5.5 moles per liter. My therefore statement is left over from my failed attempt at making this video the first time around. So therefore, at equilibrium, the concentrations of I2 and Br2 are 0.50 moles per liter, and the concentration of IBr is 5.5 moles per liter. Okay, so the ICE table helped us get that information by keeping us organized and making us aware of the stoichiometry that's going on in this reaction. Finally, to finish answering the question, B asked us to calculate a value for KEQ. So we need to write an equilibrium constant expression. So it'll be equal to the concentration of Br2 times the concentration of I2 divided by the concentration of IBr squared. So we can substitute in the values that we found. 0.50 times 0.50 times 5.5, divided by 5.5 squared. Alright, so we'll use our trusty calculators to figure that out. Times 0.5 divided by, and I get a value which is 8.3 times 10 to the minus 3. And again, there are no units on KEQ. On your calculator, that's probably 0.00826, etc. So I'm just reporting it to 2 significant digits. All right. So for you, what I would like you to try, let's see, page 451, question number 53. Give it a shot, and we'll try some more in class tomorrow.